This video is another in the series for Math 1133 for UTSA. Today we'll be talking about 12.3 optimization applications. This is something where we really could do lots and lots of examples, but we'll do just, I think I have 4 prepared for the video. We can always do more in the live session. So, global extrema is something we have to talk about. These are also called absolute extrema. The book and therefore the online homework will call them absolute extrema. I prefer to say global because of the contrast between the terms local and global. If you know what local extrema are, if that term makes sense, right, then global should also make sense. You just expand the scope of the locality, and that becomes global. So what does that look like? Well, if we had a curve like this, then we have a high point, which we would call, yeah, it's a local maximum, right? If you look nearby in the local area, this is the highest point nearby, right? Well, what if we had something like this? So a graph like that. Then we have a high point, right? And if you look locally, just sort of narrow in on it and look a little bit to the left, a little bit to the right, yeah, that's the highest point. But if you were to expand that to take up more of the graph, right, then, oh no, that's no longer the highest point in our new scope because there are these other points over here that are higher, right? So this one is only local. So I'll call that L max for local max. This first one, though, if you look locally, yeah, that's the maximum. But then if you expand your view to take up more of the graph, in fact, all of it really, it's still the highest point. So if you find a local max and you expand the view and it remains the maximum no matter how far you look, well, then that's the global max for that graph. Okay, so every global maximum is automatically a local maximum, um, but not every local will be global. Similar for local min with this one here. If I look locally, yeah, that's the lowest point, right? Nearby, that's the low one. But then if I take on the context of the entire graph, I find, oh, that is not the lowest point because over here, there are some points that are lower, right? So this is a local min. For a global max, I need a different graph. So let's go ahead and make a new graph to encompass some more possibilities. So what if I had something like this? Okay, so like a sort of a wobbly W. I got a low point here, I got a high point, and I got a low point. Okay, so this one here, this is a local minimum because if you look locally, then it is a minimum. Of course, if you look at the entire graph, it's not. This one over here, if you look locally, is a minimum. But if you look globally, if you look at the context of the entire graph, it's still the lowest point overall, right? So this one here, this is, oh, I'm going to run into the next example. This is a local max. Over here, this is both local and global. And so we'll just call it a global max with min. Definitely not maxima, minima. There we go. So this one is a global min. And while it's also technically a local min, we don't usually label it that just because calling it a global min is more specific. Every global min is a local min automatically, basically. And of course, here we have a local max. This graph does not have a global max at all, right? It's also possible if, and I might have to make more room. I have to pause the video and make room and come back to this. Maybe I made these pictures too big. It's also possible for you to have a global min or max occur in 2 places. You'll see what I mean in a second. So if I had something like this, let's say I'm going to mark a maximum value for the graph to have. And by making the graph the right shape, I can do something like this. I can do, well, we'll pretend I drew that well. Okay, like that, right? We'll pretend that's nice and neat. So I've got this maximum value here and here. So let's call this like capital M for the max value. And I have the maximum, the global max occurring in 2 places. We could call this like, I don't know, A and B, something like that, right? So you can have 2 positions tie for first place. That's okay. because there's still just the one maximum. And you know what? Let's give this a number. Let's call this 10. Just to attach a number to it. 10's a nice big number, right? Seems impressive, 10. So 10 is the global maximum. Although it occurs at two places, that's fine. That's not a problem at all. Now, one thing we want to be aware of is if I had a, I am going to pause the video and make more room real quick. Okay, so all these graphs have something in common. They're all what's called continuous. This is something that we have not talked about, this property of continuity. We have not talked about a whole lot. The simple version is that you can draw the graph with one smooth, continuous motion, unless you draw it poorly. Like this one over here. I drew in one motion without picking up the stylus at all. So this one on the right, I could have, if I were better at drawing things, I could have drawn the whole thing with one smooth curve. I would not have had to start and stop, right? That's just because I'm in an awkward angle. There's a microphone in the way. I had to start and stop, basically. Anyway, so if I had something like the following, say some curve like that, right? One nice smooth curve drawn in one motion. If I pick a couple of spots on the x-axis, say A and B, like so, okay, and these locations are these are I'm making them dash lines because they're not really line segments. I'm just representing where on the graph the x coordinate would be A and B respectively. So on this curve, I can look at this section from A to B and look at, oh yeah, it's a nice smooth graph. There are no asymptotes. There are no gaps in the graph. So when you have a graph like this defined on a closed interval from A to B, for example, you are guaranteed to get a global max and a global min. Okay, so for this one, the global max occurs right here. And because of the way I drew it, it's not an endpoint. And oh, you know what? Maybe it's over here. Let's do this. Let's have a horizontal line come out. Oh yeah, that barely beats it. This point right here at the endpoint is just a little bit higher than this point here. So our global max is actually over here. Okay. Now the global min is right here. And you might say, well, what about all this over here? But we're sticking within this segment from between A and B. So here we have the global minimum. Okay. Now, anytime you have a continuous graph, a nice smooth curve, no asymptotes or nothing weird, on a closed interval where you have endpoints, right? You are guaranteed to get both global max and a global min. Maybe it occurs in two places, potentially. But you're guaranteed to get both. Well, so what do I mean by hold on, getting ahead of ourselves here. What do I mean by continuous? No, nothing weird in the graph. So if I had a graph like this, and we won't bother, we're not gonna have to do application problems with these typically, so we don't have to worry too much about what this would look like as in a formula like f of x equals. But if you had something like this, where there's a gap in the graph, right? This is called a vertical jump discontinuity. Discontinuity. All right. This is something that in Cal 1, the course for people who go into Cal 2 and Cal 3, right? That we would spend a lot of time talking about continuity. For this class, we just need to mention it occasionally. So as long as you don't have this, this continuous would be applying to this graph, but not to that graph. That's not continuous. Okay. There are other examples of what would not be continuous, but we don't need to get all of them. Typically, what we will have will be a continuous graph. We'll have continuity. So basically, to summarize what I was talking about, this thing is called the extreme value theorem. It says if a function f is defined and continuous on a closed interval from A to B, then f has both a global minimum and a global maximum. Each one occurs at a critical point or endpoint. Okay. In the case of this example, the max occurred at an endpoint, and the minimum occurred at a local min, which is where you have a critical number, right? So we can use the extreme value theorem when we're trying to find global min and global max, and all we got to do is go to we're given some formula, f of x equals whatever, or it could be a profit function or a cost function, whatever it is, and look for the critical numbers if we have a closed interval, look for the critical numbers, and then evaluate the original function at the endpoints and critical numbers, and see, well, which location actually has the highest output. If we want a maximum, and that's our global max. If we want the global min, well, which output is the lowest? That's where the global min is. So let's do an example of that. So let's find the global extrema, that's the pluralization, of f of x equals 4x squared plus 36 over x on the interval 1 to 6. Okay. So the first thing is, do we have a closed interval? Well, yeah, from 1 to 6. We're including the endpoints. The next thing is this function defined and continuous on that interval? Well, yeah, this is a rational function. The vertical asymptote is at x equals 0. I can tell by looking at the denominator. If you plug in 0, you'll be dividing, was it 36 over 0? And you can't do that. There's an asymptote there. But 0 is not in the interval 1 to 6. So this graph, if I do a real rough sketch, it'll look something like the following. Something like this. And I'm not going to try to be precise, just a real rough graph. It'd be something like this. Again, real rough. I'm not even trying to make it accurate. But then we're only looking from here to here on this section. Okay, so that's continuous on that interval, right? And we shouldn't say, oh, so the answer is 1, right? The maximum is right here, correct? And the minimum, sorry, not the answer. I was thinking about maximum only, but the max is at 1 and the min is at 6, right? Well, no, this graph is not meant to be accurate. I don't know what the graph looks like necessarily. Using algebra, you could graph the function and look at it. That's not necessarily the best way to do it. In part because, well, how are you going to find? I mean, the endpoints might not necessarily be where the local min max are. It could be at a critical number, and algebra is not really going to be very good at helping you find critical numbers. You really need calculus for that. So basically, I'm going to rewrite this function to help work out the derivative, because this function as is, I would have to use the quotient rule, which is fine. There's nothing wrong with that. But if we do a little bit of algebra first, we can rearrange this so that we don't need the quotient rule. So I'm going to separate this into, well, I'll do it here, I guess, into two fractions, 4x squared over x plus 36 over x. And of course, this will reduce. 4x squared over x is just 4x. And this one I can write using an exponent rather than fractions. So this is 4x plus 36 times x to the negative 1 power. Okay. Then I can find the derivative of this. That's step 1 in finding critical numbers. So f prime of x, this equals 4 minus 36x to the negative 2 power. Okay, which I'm going to want to rewrite. I don't necessarily have to, but at some point I may want to rewrite it like this. 4 minus 36 over x squared. That may become useful. So step 2 in finding critical numbers is I want to look for where is this undefined. Okay, and in particular, I need to think about where is the original function defined, but the derivative is not. Because if I look at the derivative, look at the denominator, oh, 0. This is undefined at 0. But we don't necessarily need that number for two reasons. One, it's not a critical number because neither is the original function defined there. So 0 is just not a critical number because there's an asymptote. But also this interval, 0 is not in the interval. So 0 is not going to be a useful number for us anyway. So I'll say 0, but that's not in the interval. I could even just write not in the interval or nowhere in the interval. But I'll say x equals 0, but that's not in interval from 1 to 6. Okay, or I could have just written the interval. That'd be fine. So now I'm going to look for where is the derivative equal to 0, because that's where I might have critical numbers, somewhere in the interval perhaps. And there's a couple ways to get started with solving this. Maybe the easiest way would be to add the fraction on both sides, 36 over x squared. And then I can multiply x squared on both sides. And you might see where this is going. Now I can divide by 4 on both sides. So think about the solutions to this equation, right? X could be 3 or -3. But -3 is not in the interval, so I don't need it. So you might notice that in some ways this is easier. We don't need to talk about 0, it's not in the interval. We don't need to talk about -3, it's not in the interval. It's sometimes these problems are easier because they're more focused on just what's in the interval. So I look at my one critical number, and now I can apply the extreme value theorem. And all that says to do is take both endpoints, 1 and 6, and the critical number, 3, plug them into the original function and see what you get. So we'll do a f of 1. The order doesn't matter, but I'll do them in numerical order, increasing order. F of 3 and f of 6. Hopefully I have plenty of room here. So my function was, and I can use either version. It doesn't really matter. I'll go with the this version. So 4x squared plus 36 over x. 4 times 1 squared plus 36 over 1. So that's 40. So then 4 times 3 squared plus 36 over 3. Right, so that's going to be, is that 24? Yeah, 3 squared is 9 times 4 is 36 plus 36 is 72 divided by 3 is 24. And then 4 times 6 squared plus 36 over 6. Okay, so I'm going to have 36 times 4 plus 36. You know what I'm going to do? This might seem a little odd. I'm going to factor a 6 out of the numerator because I'm getting big numbers, and I kind of want to avoid that. If I can avoid using the calculator, I will. You know, it's literally like 2 inches from my elbow, and that's really far to reach. I don't want to strain myself. Okay, so 24, so 30, right? 30. So here is our global max. And then here is our global min. And this endpoint, well, it's nothing. It's in between, so we don't need it. It's not something we're looking for. So that's pretty much it. Sometimes these are relatively straightforward. Depends on the function and the derivative that you need to find. And how many critical numbers do you find? In this case, just the one. All right, let's go to the next one. This is sort of a non-example. And I kind of went back and forth on how to phrase it. Do I want to call it a non-example in the question itself? So this one says, find the global extrema of f of x equals 4x squared plus 3x plus 36 all over x minus 2 on the interval from 1 to 6. And what you might notice is that if you think about this function, it's got a vertical asymptote at x equals 2, right? 2 is not in the domain. So that means that the function is not continuous on this interval. So if we do like a real quick sketch, and I'm going to make this one just a little bit more accurate than the previous one. It's not super important to do that, but it'll be something like this. We got a vertical asymptote there at 2. And then we're going to have, what would that be? Like something like this. I'm kind of partially making that up, but something like this. This is sort of an educated guess, let's call it. And this is actually a little bit more like what the previous one would look like. It's just that we weren't going to solve using the graph. So this one says, oh, we're going to go and use from, say, 1, which is like maybe, I don't know, here, to make that up, and up to 6, right? I'm making this up. So take this part of the graph and this part of the graph. And where's the global max and where's the global min? Well, those arrows mean that the graph keeps going. So this keeps going down forever. There's no global minimum, right? And this graph is not defined on, it's not continuous, defined and continuous on a closed interval. So because we have an asymptote in the middle of the interval, we can't apply the extreme value theorem. And it turns out with this one, we're not going to get anything. So don't worry about being able to identify that. I'm not going to test you on, oh, do you know how to tell when to apply the extreme value theorem? Don't worry about that. I'm not going to give you problems where the interval doesn't work. On a test, at least. On the online homework, there might be some that ask you to identify whether or not the theorem applies. That's a possibility. And all you would be doing is looking at, well, what's the domain of this function? And is the domain does it include this, right? Are there any numbers in the interval that are not in the domain? If yes, well, then we can't really solve this problem. So at least not with the tools that we have in this course. So again, don't worry too much about that happening, but I just wanted to point out what it would look like if that did occur. But again, the kinds of problems that we'll deal with in this course, that's not going to happen. Okay, so this is a little more indicative of what we would get in this course. So let's say we have some profit function. If you make X number of widgets, you get, or well, X thousands of widgets, then you're going to make P thousands of US dollars, right? So the problem is to maximize the profit function with, probably the problem got cut off. Okay, I'll put it here. Let's say P is from, say, 0 to 100. Okay, that's the, I wrote with and I forgot to put it in. With 0 less than or equal to X less than or equal to 100 is what should have been there. That's okay, though. So in other words, our interval is 0 to 100. So the first thing is this function defined and continuous on this interval? And basically that means, does the domain of the function contain the interval? Or in other words, are there any numbers in the interval that are not in the domain of the function? And the answer is no. Well, this is a cubic function. It's a polynomial, and the domain of a polynomial is always all real numbers. So this would work for any closed interval. We don't have to worry about, oh, is there an asymptote? Nope, polynomials don't have asymptotes, so we don't have to worry about that. Anyway, what I now need to do in order to find the global maximum to maximize the profit is to say, well, what's the global max of this function? So I need to find the derivative. So step one, in finding critical numbers, I'm going to find p prime of x. Okay, so this will be 20 plus 4x squared minus 1.5x cubed. Okay. No. Got my exponents wrong. 4x minus 1.5x squared. There we go. Yeah, okay. Almost made a big mess there. So step two, well, I want to look for where's this undefined, which we've kind of already addressed to some degree. Because I said a moment ago, the domain of any polynomial is all real numbers. Well, this is a polynomial, so the domain is all real numbers. So nowhere. Okay, so now I'm going to look for where's the derivative equal to 0. Okay, so now I need to solve this equation. And because I have a decimal number here, I'm probably not going to solve by factoring. One thing I could do is multiply both sides by 2, double all the coefficients, and maybe, if I'm really lucky, I'll get a quadratic function, or quadratic equation rather, that factors. Probably not. I'm probably not going to get lucky in this respect, but it's worth checking. So let's try applying the AC method. So negative 3 times 40 is negative 120. Does this... Oh, wow. It does. Okay. I chose these numbers randomly. This is not intentional. So 20 and negative 12 multiply to make negative 120. Oh, they don't. I was thinking about 240. Okay, well, that's fine. So, well, you know what? Let's check all the options. So this is not a good factorization, but this would be, but that doesn't give you 8, right? So how about, I don't know, say 12 and negative 10? No, that also doesn't work. How about, I guess, would 15 and 8 work? Yeah, 15 and negative 8 almost works, but not quite. So yeah, my first instinct was right. Since I picked these numbers randomly, these coefficients, this is not going to factor out nicely. So at least if it does, I'm not seeing it. So let's go ahead and use the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so this is negative 8 plus or minus the square root 64 minus 4 times A times C would be negative 120. We already worked that out, actually. 120 all over 2A, which is negative 6. Okay? So, negative 8 plus or minus the square root. So this is a 480. It's positive 480, right? So plus 64 would be, what is that, 544, I think? Let's get a calculator and check. I think that's right. 4 times 120 plus 64. Yeah, 544. Okay. Which is not a square. So that's not going to give me a whole number. If I went through this process and I did get a whole number here, that would mean that factoring was going to work and I just gave up too easily. But that didn't happen in this case. Okay. So, one thing I'm going to do is I'm going to ask, can this reduce? I suppose I don't need to. I can just go to decimal numbers, but I'm going to see if maybe this reduces. This is divisible by 4. So this equals negative 8 plus minus the square root of 4 times 136. I believe that's right. Again, we'll go to the calculator in a second. Yeah, that's right. Over negative 6, so that 4 can come outside, so negative 8 plus minus 2 root 136, which itself is divisible by 4 as well, in fact, which we'll take care of that in a moment, over negative 6. So I can factor negative 6 out. Oh, negative 2, rather. Sorry. This is maybe not necessary. We could just be using a calculator to do all this for us. Okay, so probably almost out of room. Yep. So way up here, I will say, okay, x equals 4 plus or minus 2 root 34 over 3. Okay. And then we'll get some decimal approximations for this. So 4 plus 2 root 34 over 3, I get 5.221. And then also negative 2.554. Now, of course, I don't want negative values, right? Because how am I going to make negative widgets? So just get rid of that. We don't need that number. So x is about 5.221. So now, since I have a closed interval, I can apply the extreme value theorem and just check the original function at each of the endpoints of the interval and at the critical number. So f of 0, f of, let's say 5.221. I'm not going to want to try to deal with the exact value in a cubic function. That'll be really, really messy. And then f of 100, which maybe I should have chosen a smaller number, but that's fine. So f of 0, well, let's copy, put that there. P for profit, of course. So if you plug in 0, of course, these terms will all be 0, right? So we get negative 5. Like, it's no surprise that if you make no widgets, you'll be losing money, right? So if you plug in 5.221, and I'm going to run out of room here. We'll throw that in the calculator. Negative 5 plus 20 times 5.221 plus 2 times 5.221 squared minus 0.5 times 5.221 cubed. We get about 82.778. And since the function is in terms of thousands of US dollars, okay, this would be $82,778. Okay. And then P of 100, well, this is going to be a pretty large number, as you might expect. So, well, large size, I should say. We'll see what I mean by that. If you don't already suspect what's going to happen, you'll see soon. In fact, let's zoom in. So, 100, which that's a big 2,000, right? Plus 2 times 100 squared, so plus, what was it, 20,000? So pretty big. Minus 0.5 times 100 cubed. 100 cubed is a million, right? And we're not going to need to round here. So negative 5 plus 2,000 plus 20,000, yeah, minus 500,000. We get negative 478,005. So yeah, definitely not going to maximize your profit that way. This would be a way to minimize your profit. This would be the global minimum. And this one here, this is the global max. Okay, so the original question was maximize the profit. Okay, well, that means that you want to make 5.221 in widgets, but that widgets are in thousands, right? Thousands of widgets. So you're going to make/sell, of course, 5,221 widgets. And your profit should be about 83,000. Okay, so this is more emblematic or indicative of what we'll be doing in homework assignments and in exams, um, as opposed to the previous examples where, well, I'm sorry, as opposed to something like this where it's a trick question, you can't do it with the tools we have. That's not going to happen. You'll either have something like this where it's not an application problem, it's not attached to anything. There are no widgets. It's just here's a formula, find the maximum. That's gonna be some of them. And then we'll have some where it's, well, this represents something, find the maximum or minimum or whatever. So let's do some more of these. Let's do a variation on this. So given c of x below, this is a cost function. Minimize the average cost on the interval 0 to 60. C of x, this equals 0.001 x cubed plus 3x plus 100. X is in thousands of widgets, and C of x is in thousands of US dollars, okay? So what the interval is saying is that we have to make at least 0 widgets, and we can't make more than 60,000 widgets. Makes sense? Now notice that we're not finding we're not minimizing the cost, we're minimizing the average cost. As you may have noticed before, when we maximize profit, we really were dealing with the marginal profit function. We found the derivative of profit, that's a marginal profit function, which is why we talked about those before. So we could talk about maximizing. Here, we want to minimize the average cost function. So I have to come up with the average cost function from the cost function before I can get started. And then I'll be dealing with really the marginal average cost function, which is kind of why we dealt with that before, so that at this point in time, we can deal with minimizing average cost. So C bar of x, this equals C of x all over x. Okay, so this will be 0.001 x cubed plus 3x plus 100 all over x. We can split this up into several fractions, as we did before. So that over x plus 3x over x, and you may see where this is going already, plus 100 over x. Okay, and then that will then be, let's put it over here, 0.001x squared plus 3 plus 100 times x to the negative 1 power. Okay, now something to consider. We are not going to be trying to apply the extreme value theorem to this function. We'll be applying it to this function. And this function has x to the negative 1 power, which came from dividing by x. So we need to think about, well, what's the domain of this function? Is my function defined and continuous on the interval I'm being asked about? Well, now I can't plug in 0 to this average cost function. So the answer is no. This function is not defined and continuous on this interval, which kind of presents a problem because now I can't apply the extreme value theorem, which typically is relatively easy to deal with, easier than trying to do something with local min max anyway. Now there are basically two ways around this. One way is to not use extreme value theorem and use something else called the critical point theorem. But I think I want to reserve that for a later example. So we're going to find a way to go ahead and use extreme value theorem anyway. So, the reason we can't use 0 is because, well, you can't have an average of no things. How do you average no test grades, right? How do you average no heights or weights, right? So really, we should be storing our interval somewhere else. We can impose a realistic limitation. Say, well, really, we wouldn't even consider an average making no widgets. We might consider an average making 2 widgets or 1, perhaps. If you averaged one thing, you get just the one thing. But you might say, well, let's say we're not going to worry about an average unless we have 2. You could do that, but let's go with 1. So let's say, well, what would 1 widget be in terms of the variable? How would we represent that in the interval, right? Since the x coordinate is in thousands of widgets, if we want to refer to 1 widget, that would be x equals 0.001. So what we can do is we can go back to this interval and say, well, okay, maybe it didn't make a lot of sense to start there. Let's start here, 0.001. That's really our interval, okay? And then here we can say, well, our interval is 0.001 to 60. So then this represents 1 widget, and this represents 60,000 widgets. That's one way to get around it. So let's go ahead and do that. So now I can apply the extreme value theorem. So I need the derivative because I need critical numbers. So c bar prime of x is equals, and I just find the derivative of this guy here, just using the power rule. So 0.002x plus 0 minus 100 x to the negative 2 power. Okay. Now I can look for my critical numbers. So where is this undefined? C bar prime of x undefined? Question mark. Well, nowhere, because not in this interval anyway, right? Sure, you can't plug in 0 to x to the negative 2 power, but 0 is not in our interval anyway. So nowhere in the interval. Nowhere that we care about, right? So now I can look for where is the derivative equal to 0. And of course, I don't have to write this plus 0 every time. Okay. And so this can be solved somewhat similarly to the previous example. I'll add x times, rather 100 times x to the negative 2 power on both sides. And I guess I can leave this as a decimal. It doesn't really matter, I suppose. And then I can rewrite the left-hand side as 100 over x squared. And I guess the right-hand side I'll write as 2x over 1,000, I suppose, or x over 500. Yeah, that's the same thing. You could think about cross-multiplying. Multiply 500 on both sides, so it shows up on the left, and then multiply x squared on both sides, so it shows up on the right. So we'll have 50,000 equals x cubed, right? So x equals the cube root of 50,000. I hope I'm not missing a 0 somewhere. What is that approximately? We might want a decimal number for this at some point. So 50,000 raised to the 1/3 power. So I get 36.840. Okay. So there's my only critical number in the interval. So now I can apply. I'm almost out of room. I got a little bit of room left. Not a whole lot. I'll go over here. Step 3, extreme value theorem. Okay, so I can apply the original, not the original, the average cost function to each endpoint and to the critical number. So C bar of 0.001 equals, and then C bar of 36.840, and then C bar of 60. Okay. So C bar, and which one I use doesn't really matter, I suppose. I'm going to use this one just because I think it'll be just a little bit easier to write it out. So 0.001 times 0.001 squared plus 3 plus 100 times 0.001 to the negative 1 power. Okay. Throw that in a calculator and get a decimal number. So 0.001 cubed essentially is what first term is. Plus 3 plus 100 divided by 0.001. So I get 100,003. That's the average cost per widget, which is kind of high. So then I'll look at 0.001 times 36.840 squared plus 3 plus 100 times 36.840 to the negative 1 power. So my calculator, 0.001 times 36.840 squared plus 3, that should be 100, not 10. There we go. Plus 3 plus 100 divided by 36.840. And I get 7.071. 2 actually, if I round. 7.072, yeah. Okay, let's try 60. So 0.001 times 60 squared plus 3 plus 100 times 60 to the negative 1 power. So 0.001 times 60 squared plus 3 plus 100 divided by 60. So you get 8.267. Okay, so this is very clearly just a huge number. These are both small-ish, but this is my global minimum. This is the lowest value that the average cost function takes on. So to minimize average cost, then I want to make about 8,267 widgets. I think I read this correctly. Yes. 8,267 widgets. And be careful in the online homework. The problem might want several things. It might want just the X value. So you put 8.267 potentially. It might want the number of widgets. So you have to put 8,267, right? It might want to know, well, what is the minimum average cost? What's that amount? So that's going to be this. This is in thousands of US dollars per 1,000 widgets, right? So the average cost would be this would be $7,072. I didn't keep the cents, but that's okay. Per 1,000 widgets. Right, that was the scale of the the function, the variable, right? Thousands of dollars and thousands of widgets. Okay. So that would be $7.072 per one widget, right? You could round that to $7.07 per widget. Right? If that was what the problem asked for. Okay. So last example, and this one doesn't have a paragraph attached to it. This is a problem that I enjoy doing. I basically do it every time I teach calculus. I can show you how this can be a really useful thing. This is not an easy problem, but we're going to walk through it. So let's say you've got a utility company here at point A on a coastline, and we'll assume to make the problem easier that it's a perfectly straight coastline. Maybe it's in Dubai or something, right? And we've got an island. Some wealthy person lives on an island, and they need a utility line run. Maybe it's water, desalinated water. Maybe it's electricity. Maybe it's whatever. Maybe it's they want like Google Fiber run to their private island, and the local access point for Google Fiber is there, right? Let's say that this is 12 miles apart along the coastline, and that the island is 5 miles off of the coastline. Okay. Now, one option is to just run. Let's change colors here. Is to just run under the water directly to their island, whatever that would be under the water, right? I guess that'd be 13 miles if you use Pythagorean theorem, right? 5, 12, 13, Pythagorean triple. But that might be really expensive because putting underwater is really pricey. So we'll make up some numbers in a second. And then they could go all the way. In fact, let me change my stylus here so it's a little bit more visible. They could run all the way along the shore, make a right turn, and then go to the island. This will also be the longest path, right? Now, of course, you could, I don't know, go off and around, but that's not going to be efficient, right? Or you could go past the island and then backtrack, but that's not going to be efficient, right? So, of course, somewhere in the middle, there might be a place that's the most efficient to turn and go to the island directly part way through. So, go along the coastline part of the way and then turn and go directly to the island after that point, right? And so you could ask, okay, what would minimize the total cost to put this thing down? So let's say the following. Let's say that the along the coastline, so along the coast, let's say this costs, I'm gonna make up numbers. Let's say $10,000 per mile. Maybe is that realistic? I don't know. I'm just making up numbers. Let's say under the water, let's say it's twice as much, 20,000 per mile. Right? I don't know that's realistic. I'm just making up numbers. So let's say that based on this diagram that you know we need to develop a function, a total cost function. So we need to say, okay, c of x, right, equals, well, something, right? Well, what's x? I'm kind of getting ahead of myself a little bit. But we need some variable. So what should x be? X has to be something. Well, I could say, if I wanted, I have options. I could say that x is the length of the first section. I could say that x is the length of the second section. I could try saying that x is the angle there, but that's probably gonna be way complicated. So let's not do that. What's gonna turn out to be the easiest, it turns out, is to say that x is the section of the shoreline that we do not build on. That makes the algebra a little bit easier. Okay, so I'm gonna go in here and label, I guess like this. This is x. X is the section of shoreline that we do not use. Okay. Now, if the whole shoreline from A to C is 12, then that means that the section of shoreline that we do use is 12 minus x. Okay. Now, I'm going to do a little bit of the geometry involved, just cut to the chase and say, well, that means that this, change colors here, this section here, the water section, this is going to be the square root of 25 plus x squared, or in other words, x squared plus 25. So I'll skip some of the algebra for us and just do that by fiat. So that means that the total trip is going to be 12 minus x plus the square root of x squared plus 25. But the 12 minus x is cheaper per mile. So we want more of that, right? But should it be entirely that section along the shoreline? Like where should B be located, right? So let's work that out. So based on these two things, the total cost, I'm just calling C for cost. I could call it T for total, but that's fine. This is going to equal the coast portion plus the water portion, right? Now the coast portion is 10,000 per mile, and the distance is 12 minus x miles. And in fact, let's do this in terms of thousands. So let's say that this is 10 times 12 minus x. It's the coastal part. But we'll multiply by 1,000 later when we get the actual cost. Plus, well, the water part, that's going to be 20 times this distance. So 20 times the square root of x squared plus 25. So this function describes the total cost. X is the coastline not used in miles. And then C of x, this is a let's say this is thousands of USD. Okay. So now we can forget all about that and just solve this, right? Just find the minimum. Well, let's think about the domain a little bit. And the way we approach this depends. There's a couple of things to think about. What numbers can x be? Could x be 0? Could x be 12? Right? 12 is the total distance from A to C. So if x is 0, remember x is the cosine not used in miles. If x is 0, that basically means that we're going all the way from A, using all the cosine, and then turning and going to the island. Okay. And you could argue that x could not be 0 because if you turn the corner here at C, then you're using that part of it, right? Like x would have to be, well, you could say, there's two ways to say it. If you go all the way to the corner, then you are using that and x is 0. Another is, well, if you're turning there, well, you're not using that location. Like where's the cutoff point? If x was 12, if you were not using all of it, you're making a straight line. But you could argue, yeah, but if you're even building here at all, you're using part of the coastline. So could x be 12? You could say that, well, no, x could be 0, but it can't be 12. Or you could argue, no, it can be both 0 or 12. Either is fine. And that's up to you. But let's do it this way. Let's say that I don't know if x is able to be 0 or 12. I'm going to say that x is between 0 and 12, but I don't want to allow it to be either one. Okay. If we allow x to be 0 or 12, either one, it could be not both at the same time, of course, but either one is allowed, then we have a closed interval. We can use extreme value theorem. If we don't allow these endpoints, then we can't use extreme value theorem. And that's really up to us. So what I think I want to do is, here in this case, I will do the version where we do not include the endpoints. And then during the live session, if someone wants to see, yeah, but okay, but if we did include the endpoints, how would it go? What would we do in that case? Because we haven't really done one where you don't get to use extreme value theorem. That's why I want to exclude the endpoints so that we see what it looks like to do it that way. Okay, so I'm not going to be able to use extreme value theorem. So I'm going to have to use what's called the critical point theorem, which I'll explain once we get to that point in the problem. I'm basically looking for a local min, and then I'll justify afterward why, oh, this local min, this has to be an absolute or global min as well. So step one, I need to find some derivatives. Well, actually, I'm going to distribute this first. This is 120 minus 10x plus 20 times the square root of x squared plus 25. Okay, so step 1, c prime of x, total cost. Well, this will be negative 10 plus, well, I'm going to have to use the chain rule here, right? In fact, let's do it this way, right? Square root function is the same as having your input to the 1/2 power. So I apply the power rule. I will get 20 times 1/2, so 10 times x squared plus 25 to the negative 1/2 power times the derivative of the inside function, 2x. Okay. So step 2, where's this undefined? Question mark. Well, because we have a root, and in fact, this could be rewritten as negative 10 plus, let's say 20x over the square root of x squared plus 25. Because we have a root and we have a denominator, we need to think about, oh, okay, well, is it possible for that denominator to be 0? Well, if you think about it, you pick a number and square it and add 25, you can't get 0 that way, nor can you get a negative value. X squared plus 25 is always positive. So this will work for any x value, not just the ones in our interval, but there's no way to get a negative or 0 in that radicand inside that root. So no, it's not undefined anywhere. And not just not in the interval, but just nowhere in general. Nope, not going to happen. So now we can look at finding out where the derivative is equal to 0. This is part of the reason I chose to go ahead and write this like this. I think it will help solve the problem. So 0 equals negative 10 plus 20x over the square root of x squared plus 25. Okay. So it might not be obvious what to do, so I'll just go ahead and get started with what I think we should do. I'll point out that although I've done this problem before, I've made up new numbers, so I don't know what the final answer is going to be. I know more or less what to do with it, but I don't already know what the result is going to be. So I'll add 10 to both sides. And that's not necessary to start with, but I think it's probably the easiest way to start. And then I will multiply both sides by the square root of x squared plus 25, because I don't like having a fraction like this. So 10 times the square root of x squared plus 25 equals 20x. Okay. Next, I'll divide by 10 on both sides. So I get 2x. Okay. And you may already know right away what to do next. You might see, oh yeah, this is not hard. We'll just do such and such. So I'm going to square both sides. And the reason is that will get rid of the root. What we do have to be careful about, though, is that squaring both sides on a radical equation can introduce extraneous solutions. So we do have to watch out for that later in the problem. So on the left, we'll just have x squared plus 25. And on the right, we'll have 4x squared. Okay, so I can subtract x squared on both sides. And then divide by 3. And that means that x equals the square root of 25 over 3. And I'm not including a negative value because that's not in the domain that, for our function. So this is 5 over root 3, which we might want a decimal number. I think in the past, I would choose nice numbers ahead of time so that we didn't have a weird decimal number, like a root involved. But that's not necessary. It's okay to make up random numbers and see what we get. So this is about 2.887, approximately. Now we're not done, because it's possible this represents a maximum. Maybe the minimum is in an endpoint. I really don't know, so we have to check. Like I said, I made up numbers, so I don't know how this one's going to work out. I know that with different numbers, the ones I've used in the past, that this number does give you the minimum, but that doesn't mean it will always do that. So now we have to talk about the critical point theorem. Basically, I need to go do the first derivative test. So step 3, first derivative test. I could use a second derivative test, but not with this function. It would be too messy. So I got my critical number, and I'll mark it here on my number line. And I'll go ahead and use the decimal number. Well, no, I don't need to do that, actually. So my critical number is 5 over root 3. Oops. 5 over root 3, which is approximately, was it 2.8 something? 2.887. Okay. Now my interval only goes from 0 to 12. And I can't really pick numbers outside of that because it wouldn't make sense in the context of the problem. So I'll pick 1 over here, and I'll pick a 10 over here. And I check these in the derivative. So I'm looking at not C bar, sorry. C prime of 1. What is that equal to? Well, there's C prime right there. So negative 10 plus 20 times 1 is 20 over square root of 26. That seems negative, but we should check that out. So negative 10 plus 20 divided by the square root of 26. Yeah, it's about negative 6. That's negative. So the graph goes down there. And then C prime of 10. So negative 10 plus 200 over the square root of 125. Okay, so what's that equal to? So negative 10 plus 200 divided by the square root of 125. That's positive. It's about 8, 7.9. Okay, so we get graph goes down, something happens, graph goes up. That means we have a local minimum at x equals 5 over root 3. Okay. Well, we're not done yet. That's a local minimum. As we talked about earlier, local does not imply global. Like this, there might be some other place on the graph that's lower than this. How do we know that there isn't? Now, there is a way to know that, of course. So let's talk about that a little bit more. So some books don't name this anything, but the book we're using calls this the critical point theorem. If you have a graph that you know looks like this, okay, in some interval, and you find that there's a local min, then the question is, how do you know whether there's more graph over here that's lower? How do you know that? Is it possible that's true? Because if it is, that's not a global min, and that's not your answer. And so here's the reasoning. In order for this to be a continuous graph, this would have to do something to get over there. But wait a minute, that's a maximum. That's another critical point, right? But when we found our critical points, we only got one, right? So on this interval, because there's only one critical point, there can't be any others because there's only one. And therefore, this situation can't happen. There's no way for you to have, let me even make this a little more on the nose. Let's get rid of that, get rid of that, get rid of all that. How do I know that there isn't some point over here, single point, that's lower? Well, because the graph would have to do something to get down there. There's another critical point. There's a local maximum there. But we know there's only one, so this can't happen. So basically, the critical point theorem says if you are working with any interval, but you have a continuous function, so you have f as a, well, not f, but let's call it f. We're dealing with c, but whatever, f. So if f is a continuous function, defined on an interval, then if how to phrase it. If there is exactly one critical number, then the local extremum, if any, is also global. Because it could be you have a saddle point. That's a possibility. Local extremum, if any, is also global. Automatically, it has to be because there's exactly one critical number. So there's no way for the graph to turn around and do something else, basically. So with this one, we can conclude, oh, okay. By the critical point theorem, this is also global. So how do you minimize the total cost? Don't use 2.887 miles. Okay, so 12 minus 5 over root 3, which I'm doing that because I want the calculator to keep the decimals for me, give me a nice accurate value. Okay, so 9.113. And then the underwater section is square root of 25 over 3 plus 25. 5.774 would be the respective sections to be used along the coastline and along the water, respectively. So yeah, there you go. If we had used the extreme value theorem, this probably would have been a little bit easier, but I did want to do one that did not use the extreme value theorem.